Sextant and altitude correction. In this topic, we will discuss how to use and read the value of sextant and altitude correction. The sextant derives its name from the extent of its limb, which is a sixth part of a circle or 60 degrees. The marine sextant is double reflection instrument used for measuring angles in the same plane. The arc is graduated into degrees from the right to left, from 0 to 120, sometimes a little more. However, the limb is the only 1/6 of circle due to double instrument reflecting. The altitude corrections made to the HS sextant altitude are necessarily because the mathematical premise of celestial navigation has the observer taking a sight to the center of the celestial object from the center of the earth. Care of sextant. Always keep sextant in its case lecture at sea when not in use. If you must set it down, set it on its legs, never on its mirrors. Do not drop the sextant. Keep it moisture free. Use silica gel inside the case. Keep mirrors and arc clear of debris. Wiping the mirrors with lens paper and small amount of alcohol. Seawater spray gets on the sextant. Rinse with fresh water and dry gently with a soft cotton cloth or lens paper. Use light pressure when cleaning. Occasionally, oil and clean the tangent screw and teeth of the side of limb. When stowing for long periods, use a thin coat of petroleum jelly to protect the arc. If the mirrors need resilvering, you take the sextant to a sextant repair shop. Principles of sextant. The optical principle used in sextant is this: given that ray of light is reflected from two mirrors in succession, then the angle between the first and the last direction of the ray is twice the angle between the mirrors. This is the angle read of the arc. After the navigator shoots a star, takes an altitude. Sextant and altitude corrections. The altitude as indicated by a sextant or similar instrument before corrections are applied. It is the angle measured in vertical plane between an artificial or sea horizon and a celestial body without any correction. Perpendicularity. Cause index glass not perpendicular to the plane of the instrument. Test. Put index arm at approximately 25 degrees and check the difference at the direct and reflected image of the arc. Adjustment. Adjust the screw on the index mirror until both images of the arc are lined up. Perpendicularity. Side error. Cause horizon glass not perpendicular to the plane of the instrument. Test. Direct and reflected image of the same star should appear as one when the arc is moved through zero. Adjustment. Adjust the outer screw of the mirror. Collimation error. Cause telescope is not parallel to the plane of instrument. Test. Use inverting telescope with cross wires parallel to the instrument's plane and view the objects at least 90 degrees apart. Adjustment. Collar on the telescope, but this should not be loosened.
Index error. Caused by mirrors not being parallel when a sextant is set at 0. Usually remove mathematically methods of checking. Observe sun on and off the arc. Observe a star, make image coincident. Observe the horizon, make image continuous. Taking sight, calculate expected altitude bearing first. Take observation with the best horizon. Always swing sextant for good altitude. In poor visibility, reduce the height of the eye. Use strong shades when observing the sun. Take multiple observation of each body in poor conditions. Possible to take observation in strong moonlight but treat with care. Sextant calibration. If badly knocked, dropped, or physically damaged, the mirrors lose their reflective coating. Parts of equipment are missing. There is strong reason to suspect the accuracy of the instrument. The calibration certificate is more than 10 years old. Apparent altitude. By applying the IC and the DIP correction, we can determine the apparent altitude of HA simple plot. HA equals HS plus IC plus DIP. Determination of HO, the correction needed to convert the sextant altitude, HS to observed altitude HO, are IC sextant error. DIP height of eye, altitude refractive effects.
Additional corrections. These corrections are all that is needed under normal circumstances to determine the HO of a star. An additional correction is required if the observation is made under non-standard conditions of temperature or pressure. If we are using the sun, moon, or planets, the problem becomes more complicated. In addition to the correction we already mentioned, we must also account for horizontal parallax, Sun, Moon, Venus, and Mars. Semi-diameter of the body, Sun and Moon, augmentation, Moon. These additional corrections make HO's determination for the Sun, Moon, and planets generally more difficult than those for a star. For simplicity sake, with H stick to the determination of HO of a star. Parallax in altitude. The parallax correction allows to the difference in the altitude measured on the Earth's surface versus the altitude measured at the center of the Earth. The effect of parallax reduces with altitude. It is greatest when the body is at the horizontal parallax, and declines to zero when the body is overhead. Is an horizontal parallax, Earth's radius / distance of body. After correcting for altitude, the correction is known as parallax in altitude. Parallax in altitude, horizontal parallax cos / altitude. Parallax in altitude should be added to the true altitude reduction of the Moon horizontal parallax. Horizontal parallax is proportional to the Earth's radius. Therefore, as the Earth's radius declines with latitude, so does horizontal parallax correction. Horizontal parallax. This should be subtracted from horizontal parallax before calculating parallax in altitude.
Sextant reading. Micrometer drum sextant set at 29 degree 45.5. The main difference between using a star or the other celestial body is that calculations are carried out on an imaginary sphere surrounding the Earth. The celestial sphere working on this sphere, the distance becomes 90 degrees. Attitude. The point on the sphere corresponding to the observer is known as his zenith. A sextant is a doubly reflecting navigation instrument that measures the angular distance between two visible objects. The primary use is to measure atomical object angle and the horizon for celestial navigation purposes. Attitude correction is used to compensate for the refraction of the atmosphere is found in the front cover of the Nautical Almanac. This is added to additional corrections which are beyond the scope of the course but will be covered in this supplemental that